Thanks, Maureen, and thanks, conveners of that session. I was really inspired over the whole day to see how much we have to learn from each other and how much potential there is for new discoveries through these sort of cross-pollination and cross-disciplinary collaborations. I think that aligns really well with the theme of this last little session of the day, which is presenting a couple of the major strategic documents that have come out of the geophysics community in the past year. These have been the effort of many, and I think they really set us an interesting path forward towards these longer term initiatives. So first off, Dave Sanwell, distinguished professor at UC San Diego, is going to present a summary of the National Academy's report on evolving geodetic infrastructure. Hi, Dave.
Hello, everyone. I'm Dave Sandwell. I'm a professor of geophysics at Scripps Oceanography. And when you registered for this meeting, you had to check a box, and the box said, are you early career, mid-career, or late-stage career scientist? And I'm definitely a late-stage career scientist. You may wonder what we do as late-stage career scientists when we don't have to apply for jobs and we don't have to worry about tenure, but we have the opportunity to write reports on things like what I'll talk about today, evolving the geodetic infrastructure to meet new scientific needs. This is a report done by the list of authors that you can see here. But also there's an important list here of reviewers that are there to keep us honest for the report. So I'll talk about basically 4 topics. What is the geodetic infrastructure? Why do we need it? What improvements are needed? And then finally, I'll talk about a question that we don't have an answer to. How can we maintain the gauge network for decades? This is something we should all be concerned about, and we don't yet have a solution to this. Okay, what is the geodetic infrastructure? Well, the geodetic infrastructure consists of 4 techniques: very long baseline interferometry, satellite laser ranging, GNSS, the global distribution of fundamental GNSS sites, not all the sites, and DORIS. DORIS mainly a tracking system for satellites, mainly run by the French. So VLBI is a technique that's used to monitor the orientation of the Earth and also the scale of the Earth. And it uses 2 antennas that are separated across the surface of the Earth. They simultaneously view quasars out in space, which are fixed in the celestial reference frame. And from that measurement, you can determine the orientation of the Earth very well and the scale. I'll talk about that later. Satellite laser ranging is a technique that uses a laser to range to satellites, of course, but these are high satellites. They're not the low satellites, but they're high and they have less atmospheric drag, less sensitive to the small scale variations in gravity. And this is good for measuring the position of the center of mass of the Earth and also the scale of the Earth. GNSS that we're all familiar with is a technique that we know about. It has a constellation of GNSS satellites, and we'll talk about this in a minute. It's really important for transferring the information, the precise information from VLBI and SLR to the broader network of other GPS stations, smaller things that we have on ships and planes and out in the field. The maps down here show the distribution of these sites. VLBI is pretty well distributed across the globe. And you see that there are contributions from NASA, the red sites, and other US departments. And then the blue sites are the international contribution, our collaborators. And this is very much a global collaboration that's needed to do this activity. Satellite laser ranging has a similar distribution of sites. Again, there's a large international contribution here in blue. The red sites are the NASA sites, and there has to be some in the southern hemisphere. We'll talk about that more in a minute, why we need these sites, why we need more. This is a map of the fundamental GNSS sites. It's not all the sites, it's just the ones that are part of this geodetic infrastructure used to define the terrestrial reference frame that we'll talk about in a minute. And then finally, DORIS, as I said, it's mainly used for tracking satellites. Okay, this report was on why we need this geodetic infrastructure. And in particular, we needed to connect the geodetic infrastructure to high-level science applications. And this is a complicated diagram, and it's hard to see this connection. And a lot of times the geodetic infrastructure is invisible. But I'm going to walk you through this. At the bottom here, we have the geodetic techniques, SLR, VLBI, GNSS, and DORIS. There's also software that's really important for using these data and processing these data. We need experts and archives. And then that is used to define something called the terrestrial reference frame that I'll talk about next. And then that is used to do things like satellite orbits and improve the gravity field and so on. And so there's this connection between the fundamental measurements and the science. And we'll go into a few of these connections in this presentation. Okay, what is the terrestrial reference frame? Well, it really just consists of 7 parameters. And these 7 parameters are the position of the center of mass. 3 of them are the position of the center of mass of the Earth, and 3 are the orientation of the Earth in the celestial non-rotating reference frame. And there's a 7th parameter for scale, the distance between 2 points on the surface of the Earth. It's really important because it allows diverse geodetic measurements to be linked over space and time. And the time is really important. The terrestrial reference frame changes over a wide range of timescales as mass is redistributed over the surface of the Earth. And down below, we have 3 examples. You could have a sudden earthquake, such as the Tohoku earthquake that moves the stations on the surface of the Earth, and we have to correct for that motion. There's also an annual signal due to snow loading or other movements of water over the surface of the Earth. This has an amplitude of about plus or minus 5 millimeters. And then there's the long-term variations in the position of the center mass in the Earth that we expect to see due to melting of the ice sheets. This could be 50 millimeters, and we really need to monitor this because we could confuse the motion of the center mass with actual with melting of the caps. We want to make sure we can pin down the reference frame. Okay, here we're looking at how these different techniques contribute to the terrestrial reference frame. And for example, VLBI is really strong at determining the orientation of the Earth in the celestial reference frame. It's very strong at determining the scale, distance between 2 points. It's not so good at determining the geocenter of the Earth, and the geographic density is low, so it's not good for transferring the terrestrial reference frame to our GPS network GPS receiver we have in the field. Satellite laser ranging is not that great at determining the orientation of the Earth. It's really essential for determining the scale and especially the geocenter. Where is the center of mass of the Earth? And I'll explain why we need to know that to millimeter accuracy. And then it's not good for, it has a poor geographic distribution and so, or low distribution. And so it's not good for transferring the reference frame to our measurements. And then finally, GNSS, well, we work all the time with GNSS. We think it can do everything, but it can't. It really relies on VLBI and SLR. It's not good at determining the orientation of the Earth, and it's okay for determining the scale and the geocenter, but not especially good at those. But it's really good at transferring the really precise information we have from VLBI and SLR to our GNSS measurements out in the field, other things. Okay, let's go back and look at a detailed connection between the geodetic infrastructure, and the example I'm going to show first is sea level change. How are these two connected? Okay, so first I'll show you on this diagram, and then I'll walk you through an example. Um, we have the techniques. We use those to define the terrestrial reference frame. That's used to determine the orbits of altimeter satellites. And the altimeter satellites are used to measure sea level change. And we have to know the orbits to the same accuracy that we measure the height of the altimeter, the range measurement. So for example, here we have a satellite altimeter orbiting the Earth, and it's ranging from the altimeter down to the surface of the ocean. Centimeter accuracy, when you average over lots of measurements, you can get millimeter accuracy. But we also have to know the height of the satellite above the reference ellipsoid, or where it is in the terrestrial reference frame. Now, the issue is that the center of mass of the Earth can be changing with time due to the motion of the water over the surface of the Earth or whatever, earthquake. Um, and and that change, if we don't measure that change and understand it, that'll be misinterpreted as motion of the ocean going up and down. In other words, the center of figure of the Earth is where the tracking stations are, but the satellite orbits the center of mass of the Earth. So any change in the center of mass will cause a change in this position up here. Well, how big are these changes? Well, here's an example of the motion of the z component, that's the northern component of the center mass of the Earth, as a function of time. And you can see it's sort of plus or minus 3 to 5 millimeters, and it has a very strong annual cycle. So again, if we didn't know about this, we would make measurements of sea surface height with altimetry, and it would appear that the northern hemisphere is going up and down at this amplitude of 5 centimeters up to 5 millimeters up to 8 millimeters. Okay, so of course you all know this story. We need to understand global sea level rise. It's currently rising at about 3 millimeters a year, almost 4. This is really pretty much derived from satellite altimetry. The total sea level rise has two components. It has a mass change part due to the melting of the ice sheets and so on, and then it has a thermal expansion part. In addition to the global sea level rise, we need to know the regional variations in sea level rise because people live, for example, on islands and they worry about sea level rising right there. They don't care about the global thing. And so there are these regional variations that we need to keep track of, and that can be done with satellite altimetry. So the requirement is we have to measure sea level rise to an accuracy of about 0.5 millimeter a year, which is pretty stringent. This puts a really tight constraint on the terrestrial reference frame. Now, people really only worry about relative sea level rise. Oceanographers care about, what's happening out in the deep ocean, but people only care about what's happening on the shorelines here. And relative sea level rise has two components. It has the ocean going up and down, but it also has the land going up and down. So in addition to measuring what the ocean's doing, we need to measure the land vertical motions. And this can be done with GNSS sites, and it can also be done with INSAR, radar interferometry. But again, we need to know how the center of mass of the Earth is moving because both the GPS satellites and the INSAR satellites are orbiting the center of mass of the Earth. So again, we need to know the long-term stability of GNSS sites to about 0.5 millimeter a year. Okay, sea level change. So in the report, of course, we've gone through 5 or 6 of these scientific disciplines and come up with what we need to maintain the geodetic infrastructure and then enhancements to the geodetic infrastructure that are needed for the next decades. And to drive this home, we need to improve the TRF, terrestrial reference frame accuracy, to 1 millimeter a year. And we want to get the origin to 0.1 millimeter a year so we can do better than that 0.5 and really look in the long term what's going on. To do that, we need to improve the Z component of the center of mass. And to do that, we need to add some tracking stations, satellite laser ranging tracking stations in the southern hemisphere. We also need to install GNSS stations at all the tide gauges to get that absolute vertical land motion that's required to achieve this 0.5 millimeters a year. And there's other requirements that you can read about in the report. I want to talk about one more of the scientific applications we looked at because it's really relevant to the gauge community, and that's looking at the terrestrial water cycle. So as the water moves over the surface of the Earth, two things can happen. You can get elastic loading. So let's say there's a big drought in Western US. I'll show the example. The water gets taken away, the Earth rebounds elastically, and you can measure that with GNSS receivers. You can also see it with GRACE, but at a lower resolution. But another thing can happen when you take the water out of a sedimentary basin, it acts like a sponge and it contracts. So in this case, the GPS receivers will be going up during a drought, and these will be going down during a drought. We'd like to understand both of those processes. So here's an example of the elastic loading part. This is the vertical displacements observed by GPS in the Western US from March 2011 through March 2014. There are newer examples, and you can see what's going on here. If we just take the GPS stations that are away from the sedimentary basins, here we start with 0 deformation, and then it goes, the whole Western US is moving up, especially in areas where a lot of water is being taken out of the soil and the crust. Now, why does this matter? Well, if we try to make these measurements with typical or common ways of doing hydrology and looking at soil moisture, we only see what's on the surface. We see the snow, so we can measure the variations in the volume of water, mainly getting an annual signal, but we don't see what's happening in the soil and in the upper part of the crust. But with the GPS technique, you can see that there are these annual variations, but then at the beginning of the drought, you can see this is going down, and that's the water is going down, and you can only see that with the GPS. So it's a whole new way of looking at droughts and water storage in the soil and crust. So again, for the terrestrial water cycle, we have things that needed to be maintained and things that need to be enhanced. And the one thing that we should be concerned with is, first of all, we need to maybe add some GNSS sites, especially in areas of these sedimentary basins where we don't have good enough coverage to look at the deformation. A lot of these sites are in areas of farmland, so we can't do INSAR very well. And so we need to maybe improve the station spacing. But as I said in the very first slide, there's a problem in that we don't have a long-term solution for a U.S. agency to maintain these GNSS sites. Of course, Gage is doing a wonderful job, but it's not going to be funded forever by the National Science Foundation. Okay, so common themes for maintaining and enhancing the geodetic infrastructure. We need to maintain, in some cases, enhance the accuracy and stability of the terrestrial reference frame. And this translates into the accuracy and stability of satellite orbits. We also need to monitor the low degree geopotential harmonics because they'll change the orbits and change as water moves over the surface of the Earth. We need to augment the GNSS network to a 40-kilometer spacing for hydrology. And finally, we need to support software, models, data, and expertise young people need to get into this activity and be involved in the geodetic infrastructure. So I'll end there and take questions. And I forgot to say there's a report on this. It's free. It's at the National Academy site, and it's on the first slides.
Thanks, Dave, so much. I think in the interest of time, we're gonna flip to the next presentation and then we can have questions either in the chat window or if we have time at the end of this session for a broader discussion. So with that, I wanna introduce Ramon Aerosmith, professor at Arizona State University, and for the purposes of this session, also the chair of the portfolio review for NSF Geophysics. So Maggie Benoit mentioned this at the beginning of yesterday, that the work of this panel is really getting a lot of traction in guiding the future direction for NSF-sponsored geophysics.
Hi, everyone. Thanks for letting us talk about our report, which was entitled Recommendations for Enabling Earth Science Through NSF's Geophysical Facility, a portfolio review of EAR seismology and geodesy instrumentation. And I want to start off by recognizing the committee who worked really hard. It was a big job, and there was, sustained conversations, really great involvement among the whole committee, lots of different perspectives coming together, and a really careful effort to pull this together. And I want to also recognize and thank Maggie Benoit and Lindsay Martin from the National Science Foundation for their oversight and patience with us. And this document was prepared at the request of the U.S. National Science Foundation to the Advisory Committee for Geosciences. So that's called ACGEO, and it's the top-level advisory group for NSF's EAR and associated parts of the Geosciences Directorate. We worked on our project from July 2020 until April 2021, and the final draft was completed in early 2021 and officially accepted by the ACGEO. Seismic and geodetic instrumentation are essential infrastructure for the study of the Earth's surface, interior dynamics, history, and hazards. They're used to elucidate the interactions between the geosphere, hydrosphere, cryosphere, and atmosphere, and the observations must be sensitive to displacements over orders of magnitude of spatial range and time spans. And so the Geodetic Facility for the Advancement of Geoscience is called GAGE, and it's currently operated by UNAVCO. SAGE is the Seismological Facility for the Advancement of Geoscience, operated by IRIS, and those are supported by the NSF. And this map on the right here shows the major permanent networks of SAGE and GAGE, the most important of which are NOTA, which is a network of the Americas, which is the squares from Alaska through the Caribbean of GNSS or GPS systems. And then the other big network is the Global Seismic Network, which is the dots with circles, which is provides global seismological coverage. In addition to these particular example networks, there are many important PI-driven deployments, both permanent and temporary. So the IPRC was asked to recommend critical instrumentation and sensor network operation capabilities needed over the period 2023 to 2033 that would enable progress on the priorities articulated in the Earth and Time report and recent community consensus documents. That we're also to recommend a balance of investments in new and existing but evolved instrumentation and sensor network operation capabilities. We had budget scenarios as one set of constraints: reduced modest growth and optimistic growth. We had an emphasis on EAR supported instrumentation only, so no polar and only terrestrial deployments. And then we were subject to the FACA oversight, which meant that we weren't able to really interact with the community, but had to be representative with our own expertise, and that was unconflicted. So one of the activities we did was to sort of exercise the various reports and look at, for example, the Earth and Time and the connections with or alignment with grand challenges identified in other reports that were coming from the seismological and geodetic community. And so this shows the width of these ribbons shows the strength of connection or strength of alignment. And what we found were a number of priorities that are strongly aligned across all of the reports. Others that were more narrowly aligned but really significant and had deep connections, and those included the ones about what does the Earth's past reveal about the climate system, critical elements, and water cycle. There's a lot of details on our recommendations in the report, but our primary recommendations are these. First is expand resources to create large-scale, dense, multidisciplinary, multi-instrument seismic and geodetic networks. Maintain and strategically expand the global seismic network and the network of the Americas geodetic network. Support multidisciplinary rapid deploy sensor packages for hazardous events. Invest in emerging technologies. There's a whole chapter on some of our ideas about what could be done. Recapitalize and modernize equipment pools. Push for recognition and base support for seismology and geodesy instrumentation networks as U.S. national infrastructure. Enhance data access, exploration, utility, citability, and curation. These are essential components of scientific infrastructure. The future geophysical facility should develop a structure to embed anti-racist, non-discriminatory policy, practices, and goals, including attention to hidden biases throughout its operations. Maintain a strong and vibrant system of community governance of the facility to set high-level science and instrumentation priorities and serve as a focal point, hub, and springboard for community interaction, outreach, education, and collaboration. We know this is what has gotten us here now, and this is a major part of our success. We have to support and appreciate the professional facility staff that make this infrastructure work. We have to ease the deployment of geophysical networks that cross the shoreline. And we need to develop or expand partnerships to broaden the base of support. So here's this summary diagram that helps explain kind of the spectrum of priorities and frontiers for the systems, including the enabling technologies. So the black would be existing sensors, blue is aspirational sensors, and red is the enabling technology. And we tried to show what's high priority on the vertical axis and then what is sort of degree of frontierness or readiness on the horizontal axis. And so you see the highest priority is the geodetic and seismic networks, and then also new opportunities include distributed acoustic sensing and terrestrial gravity. And then high priority enabling technologies are telemetry is a big issue. It's a big cost. It's going to be essential to use these data more and really tackle the real-time opportunity. Also, autonomous robotic systems are key, and power supplies are going to be important. So the report contains detailed recommendations for both geodesy and seismology under the different budget scenarios. So what we have, and I won't read through all the details here, but we have these two tables of existing gauge instrumentation and existing SAGE instrumentation, and then talk about the bare minimum of the systems to under diminished or flat funding, what would be appropriate with modest growth, and then what's in an optimistic scenario. And there are many footnotes in here, as you can see, all these little numbers. And so although we've done our best with the actual numbers of instruments and so forth, we felt that it is also kind of provides a game plan or a template for how to make decisions going forward. So the report summarizes the impacts of funding scenarios compared to their current state, and these go through the Earth and time kind of topics and with their little icons, and then talk about what would be lost under reduced to flat funding, and what's gained with optimistic funding to try to make that point pretty clear. The committee felt pretty strongly that we wanted to advocate that the future geophysical facility embed anti-racist policy practices and goals throughout its operations and really value justice, equity, diversity, and inclusion. Suggestions included assessing and increasing transparency, providing training and resources, expanding the selection criteria for meeting locations and field trips, featuring indigenous knowledge of and contributions to geosciences, and improving accountability. And I do want to say that in summer 2020, IRIS and UNAVCO released statements on racism in the geosciences, and so by us saying this should be done in the future, they're doing it now. So I don't want to make that sound like a criticism. A big thing we wanted to highlight was geophysical sensor networks as U.S. national infrastructure. So these networks funded by NSF are fundamental structures and facilities needed for American society and economy to function. They should be supported as such. And they're essential infrastructure that are continuously and reliably present, can be plugged into when needed, and have a low cost threshold for users to access. So in other words, roads, railways, the internet, and we know that the template is how NSFNet and other research networks became the internet. And societal benefits include monitoring geologic hazards, real-time earthquake and tsunami early warning, weather forecasting, and national security, and then also real-time navigation. One of the interesting science topics that came up was the recognition or seismogeodesy. So this diagram shows on the bottom is sort of time, sampling time, and then sensitivity on the vertical axis. On the left is the broad seismic system sensitivity, which you see is highest for the higher frequency, and then in blue is the geodetic velocity sensitivity, which really increases for larger time scales. And so there's a gap in the middle, which could be addressed, and in that gap are important signals of phenomena from faulting, tides, magmatic processes, and surface pressure changes from hydrology and atmospheric changes. Now there are the plate boundary observatory borehole strain meters do fit in the gap, but this is an important opportunity and a recognition of the complementarity, but a place where more could be done. Distributed acoustic sensing records strain in the direction of a fiber optic cable that's comparable in signal to noise to measurements by single component accelerometers or geophones, and these systems can use existing fiber to and all that needs to be purchased is the interrogators to basically do the interferometry on the signals. But this was something that was very much enthusiastically supported by the committee, and there could be both the support for infrastructure to purchase the critical components, but also support for accessing these fiber networks, and both terrestrial and some of the biggest fiber systems are on the seafloor, but these could give us a really powerful view going forward of vibrations. And so another topic area was dirty, dull, and dangerous applications for robotic systems in the earth sciences. And we see that robotic systems offer important opportunities to advance observations of geologic and geophysical processes. Applications of these include semi-autonomous sensor platforms, sensor deployment and retrieval, and data recovery and sensor health check. And we also recognize that robotic systems represent a really important STEM gateway for geophysics. So people love robots, they love thinking about these things and playing with them. So it's a chance to make better observations, but also bring new people, new scientists into the community. And so this picture just shows some of the platforms, the sensor that can be deployed, the team here playing around with working on this quad rotor, some of the differencing that's possible by repeat imaging, and then this end-to-end simulation of these processes in the computer at the same time as the actual hardware is deployed. All right, so returning to the spectrum of priorities and frontiers, I hope this is helpful for everyone. Looking forward to the conversation. Thanks a lot for the opportunity to contribute, and thanks also to committee members here who can help with the conversation. I look forward to seeing where we can go and taking the next big steps.
Super. So I know that Bill Hammond and Ved Lickett are subbing in for Ramon Aerosmith to answer questions on the portfolio review. They both served on that committee. So there have been a few questions in the chat window. One about what does it mean to be U.S. national infrastructure, which I think Ramon answered in his talk right after the question was typed in. But then also a little bit of discussion about the importance of telemetry. So infrastructure is important, but so is a pathway to moving data from that infrastructure. I don't know, Bill or Ved, do you want to comment more on that?
On telemetry, I think we did recognize that in the report as something that was extremely important, in that the more ubiquitous and available and inexpensive and globally available that it is, the better. I mean, we talked about some specifics to that, but I think that the key thing is that the need is recognized, and it is stated in the report pretty strongly. So I would encourage you all to check it out. The report itself is available on the NSF website, so I could maybe drop a link to that in the chat.
So, there is a link to both of these reports in Pathable in the section for this session. So if you're interested, both of them are beautiful pieces of work with a lot of thought and effort going into them. And the telemetry question, I will also say that the Gauge and SAGE facilities definitely have our eye on Starlink and what that's going to mean for telemetry. It might be a game changer for how fast we're able to move data from sensor to user. But it's hard to know exactly how that's going to work right yet. Great. Any last questions? Or I don't know about y'all, but my brain is melting. Yehuda asks, can you comment on the current state and plans for co-location of Gauge and SAGE geodetic and seismic instrumentation within the current and future networks? Well, I mean, that's not so much in either of these reports. I don't know, Bill, if you want to say, I know in Dave's piece, there is a little bit about co-location.
Yeah, I mean, it's really important for the global geodetic reference frame. And I think Dave touched on that in his talk, and he might want to say a few more words about it. He's appearing, so maybe I should.
You mean about co-location of SAGE and Gauge? We didn't look at the seismology very much, mainly just the geodetic instrumentation. But I worry about this long-term support for Gauge instruments, and it's going to come up again and again because NSF is probably not going to support these things forever, and who's going to take that responsibility? So
yeah, I think that's part of the motivation behind the pitch for these instruments and networks to be national infrastructure, and that they are so important and they are so relied upon, and that the community maybe gets a little fatigued sort of getting it recompeted every 5 or 10 years, and everybody expects it to be there. Of course, it's good for it to be discussed and reviewed and enhanced and all of that, but that is, I think, the fundamental reason behind the pitch for it to be national infrastructure, and our efforts involved generating a 1-pager, or maybe it was 2 pages, but it was very short. It's something that people who work in the NSF, working in the Washington DC sphere can take with them to make pitches on the behalf of our community.
I mean, one thing I would say, just maybe that Yehuda's comment is a nice way to close out this session and this day of fabulous talks. because it just reminds us all how complementary the kinds of signals and noise that we all collect are to one another's scientific targets. So it's by locating sensors coherently in thoughtfully designed networks, whether that's co-locations or geometries that complement each other. I think that's driven by the science, but certainly taking into account a variety of different kinds of data streams and the processes to which each are sensitive is a way for us all to move forward our understanding of Earth systems. And having these persistent networks, I think, is clearly a theme of our sessions about transients. I mean, you just can't see those unless you're measuring lots of different things for a really long time. So maybe our take-home message for today is measure a lot of things everywhere for a really long time. And then let smart people have at the data streams and see what y'all come up with. All right, so there is still a very lively chat stream, and I encourage you all to continue talking all night if you'd like, but also feel free to go have dinner.
Thank you, everybody, speakers and moderators and chairs. It's been an action-packed day, so everyone should go unplug from screens now, and then we look forward to seeing you in the morning when we kicking off with the last plenary session, new approaches to processing big geophysical and geospatial data sets, which of course is super important to both of our brands of geophysics. Thank you.
Great.
Thanks,
Thanks
everyone.
everybody.